So in our last lecture, we talked about diodes as being made of a P and an N junction. And we said that when those two intersect or meet due to the growth of a P side on one side and the P side on the other, then where the two meet, they form what we call a P-N junction. And we said there will be diffusion of charge carriers around the junction, such that at the end of the diffusion or at equilibrium, there is a net positive ion charge on the N side and the negative ion charge on the P side. And we said this becomes the barrier potential, and the layer that is created is what we call the depletion layer. Then we also say that if you now connect a voltage source to the P and the N sides, you are now doing what we call biasing. In other words, you are now biasing the circuit. Then we said when you are biasing the circuit, you are forcing current to flow in one direction. So we said there are two ways of biasing, the forward bias and the reverse bias. So in the forward bias, we said the junction is forward bias, so that as we increase the voltage, the depletion layer becomes thin and disappears, so to say, in the ideal case, such that at the end of the day, you have current flowing through the PN junction. Then we said this is achieved by connecting the positive terminal of our source to the P side and the negative terminal of our source to the N side, right? Then we said we achieve reverse bias by connecting the N side of our junction is connected to the positive side, positive terminal of the source, and the P side is connected to the negative terminal of the source. Then we said in this case, the depletion layer will grow as charge carriers are now drawn away from the junction, and at the end of the day, we have a very large potential difference across the two sides. And we said this can continue until we reach the breakdown voltage at which the same conductor can no longer withstand the voltage gradient across it, and then it breaks down in what we call thermal breakdown. So today we are going to look at the diode circuits. Can you just confirm if the PowerPoint presentation is moving on your side?
Yes.
Thank you. Right, so we now look at diode circuits. When we are looking at diode circuits, we are looking at a situation whereby we connect a voltage source now to we connect a voltage source to one side of our diode so that we have a complete circuit. The resistor is a current limiting resistor so that we don't have infinity value of current flowing or a current that is too big. So R will just be for current limiting purposes. Then in this connection, since the anode is connected to the positive side and the cathode is connected to the negative side, then we see that this is already forward biased. And now we want to see how we can then analyze those diodes circuit, right? Now, in our usual circuit calculations, we know that the voltage across the resistor is IR, current times resistance. The current through a capacitor is the rate of change of voltage with time multiplied by the capacitance. Then the voltage across the inductor is rate of change of current with time multiplied by the inductance, right? But when it comes to the diode now, this is where we use the Shockley equation, the one we discussed at the end of the previous lecture. So we are saying this is no longer linear, as you can see, because it is a variable that also depends on temperature, right? So you cannot universally say the voltage across the diode is this much, and it is also a function of the voltage impressed across the diode, which is VD, right? So it will be very difficult for us to write voltage equations or current equations for that kind of circuit, right? Now, the scenarios that we meet when we look at this kind of situation is by where we have the voltage across the diode being 0. So if VD is equal to 0, it means the current is now equal to VSS over R, because VD will be equal to 0. Then we also look at a situation where VSS, which is the supply voltage, is at a maximum, right? So that the voltage across the diode is at a maximum equal to VSS. Then it means if this is VD is equal to VSS, there is no net potential difference across the resistor, and the current is now equal to 0. Now, when you draw the graph for V equal to 0 and I is equal to maximum, you get the first point. Then when you draw the other point for VD is equal to maximum and I is equal to 0, and you join those 2 points, you get what we call the DC load line for that kind of circuit. So I realize that we will deal with this load line analysis several times in this course. So what are we saying? The region that is bound by the load line in the axis will be the operating area of our circuit. That means you can get any other operating point within this region, right? Now, if you are given now the diode characteristic curve, which we said there is a value V of VD in which the current starts to increase, then you realize that where that line meets the DC load line would be the operating point for that diode, right? If you get a diode curve, if another diode maybe which operates like this, then this will be its operating point, right? So like I'm saying, it means the diode can operate anywhere within this shaded area in which VD is less than VSS to a point where VD is equal to 0, and also where I is equal to 0 to I is equal to VSS over R, looking at this equation. So that is what we call the DC load line, right? Then, looking at it that way, you will see that if there was another diode with this diode characteristic for a given circuit, then it would have defined operating points, right? So how do we get the operating points? We determine the values of the currents with respect to the circuit parameters. We find the value of the current with respect to the circuit parameters, right? So how does that work? It means if you are given a circuit where the value of VD, let's say the value of VD being equal to, let's say, 2 volts here, right? And maybe a resistance of 1 kilo ohm. So around 1 kilo ohm in that. Then you realize that the maximum current will be V over R, which will give you 2 milliamps. And the maximum voltage across the diode where I becomes equal to 0 will be 2, right? And then at any other point, depending on the value of R, you can get different values of our characteristics, right? Now, the diode that we are talking about here is a diode which will allow current to flow in one direction, in which it just flows in its forward bias direction. But there is another type of diode which is called a Zener diode, right? So a Zener diode now, unlike our rectifier diode or our normal diode, it can operate in both the positive or forward bias direction and the negative or reverse bias direction. Now, in our previous explanation, we said if the voltage across the diode in a reverse direction reaches a certain voltage, which we said is our breakdown voltage, then the diode will have thermal breakdown. That means too much current will flow and it will eventually break down, right? But then the Zener diode is designed such that it can conduct in a reverse breakdown. That means the breakdown that occurs in the Zener diode does not destroy it like it does in the rectifier or normal diode, but instead it forces the Zener diode to start conducting continuously at a certain fixed voltage, which we'll call VZ, right? So what are we saying? We are saying the Zener diode is a normal diode in forward bias. That means it has its own VD, which is usually 0.7 for silicon and 0.3 for germanium. But also, when you put it under reverse bias, to a certain point, it reaches a voltage in which it starts conducting continuously in reverse breakdown. And that is what we call the Zener diode, right? So the breakdown voltage is controlled by doping levels of the Zener diode. So in other words, it can withstand from minus 2.8 to around minus 200 volts that are in reverse, right? So what I was saying, when you are forward biasing the Zener diode, it just operates like a usual diode, whereby you just need to reach its barrier voltage, which I said is 0.7 for silicon and 0.3 for germanium. Once you reach that voltage, it starts conducting continuously and tends to maintain that voltage as long as it's in forward bias. The Zener diode will get into breakdown when it reaches breakdown voltage, which can be in this range depending on the doping. Then it will maintain that voltage while the current will be increasing across it. That's the characteristic of our Zener diode. So this is the symbol of our Zener diode, right? It's just a normal diode with kind of a Z in that direction. And its forward direction is this. So this will be the anode, and this will be the cathode. The cathode negative, anode positive. So I'm saying if you connect it in this forward bias, it will just reach any one of them depending on the same conductor that has been used, and then it maintains that voltage. But then we're also saying if you put a positive on the cathode and a negative on the anode, We are reverse biasing this Zener diode. All you need to do is to reach its breakdown voltage. Once you reach its breakdown voltage, it maintains a voltage equal to Vz across it while the current will be increasing, right? So the major application of the Zener diode is to provide an output reference that is stable despite changes in input voltage. So what you are saying is once you reach its breakdown voltage, the Zener diode will maintain that voltage even though this voltage Vs will be increasing. Then that means it will just be dropping across the resistor, and the Zener diode maintains a constant voltage across it. And we are saying it does that when it is in a reverse bias. So sometimes the circuit that produces constant output voltage while operating from a variable supply voltage is needed, and such a circuit is called a voltage regulator. So since we said that a Zener diode now will maintain a voltage which is equal to its Zener voltage, then even if the voltage here changes, it will maintain a constant voltage, right? So the Zener down is a breakdown voltage equal to the desired output voltage, right? So we are saying if you need 12 volts, you just need a Zener diode with a Vz equal to 12, then you connect it in reverse bias and it will maintain that voltage. So the resistor limits the diode current to a safe value so that the Zener diode does not overheat. So like we are saying, the Zener diode will also have a limit to the amount of current that it can withstand, right? So it will allow a certain amount of current, which if it is biased, it will then thermally break down. So the resistor will now be used to keep that value in a safe range, right? So this is our example. I'm not sure, it seems my circuits are not loading. I don't know what happened. Okay. Let's just proceed. We'll use the example at a later stage. So what are we saying? We are saying there's a certain voltage which if we reach, right? So in this case, it is 10, which is our Vz, and here it's minus 10.5, right? And then given a circuit with a value of R and a value of Vd, you can determine the maximum and the minimum current that can flow. The only thing that you have to take note of is that the currents are in the negative direction relative to what we use here because we are reverse biasing the diode. So the value of Vz here, then Vss minus Vz will tell us the current that will be flowing in that situation, right? So the Zener diode will now be able to maintain its voltage over a range of currents that you get there, right? Then in a complex circuit, we are not going to deal with this anyway. All you need to do is get Thevenin's equivalent circuit, then determine what happens to the diode circuit. In other words, you can have a complex circuit which contains another components. Just reduce that circuit to Thevenin's equivalence circuit, and then you can analyze it as we have been explaining before, right? So if you are given that a Zener diode curve is like this, VSS is equal to 24 volts, which will be our supply voltage in this case, right? We are looking at 24 here. The resistor being 1.2 kilo ohm resistor, and RL being 6 kilo ohm resistor. We want to find the load voltage VL and the source current IS. We want to find the load voltage, which is VL, and the source current IS. right? Now, if we look at our VSS, we said our VSS is equal to 24 volts, and our source current is IS, and we are given this diode characteristic. So this is its DC load line, right? DC load line. And this is characteristic F. So this is our operating point for what? For our diode, right? So what does it mean? It means the diode reverse voltage is what? Is 10 volts, right? Can you see that? For this kind of diode given, it means this is its operating point, the intersection point of the diode characteristic curve and the DC load line. That will be the intersection, right? Then, if this is 10 volts, right? Then, what is the load voltage? Automatically, it's determined by what? By this value. Then what is the current? It will be 24 minus 10 divided by the resistance, the overall voltage across the resistor over the current, right? And that is what you get, right? That's the operating point there. Then also given the circuit of Zener diode is shown, find the input, the output voltage for IL is equal to 0, IL is equal to 20 milliamps, and IL is equal to that. Sorry. So again, we are looking at a situation whereby the load current is already given, right? And we have the Zener diode characteristics, right? So our operating points are the intersections of our Zener diode. We have this point and that point. Then at IL is got 20 milliamps, so that's our point. IL is got 10 milliamps, that's our point. Then IL is got 0, that's our operating point, right? So writing the Kirchhoff's voltage law equation for the loop consisting of the source, the resistor, and the load, we obtain 15 minus 100 IL minus ID, right? Remember, current entering is not current leaving. IL minus ID minus VD should be equal to 0, right? Then you can now use that, using the given values to get your required output voltages. So at the intersection of the load lines with the diode characteristics, we find V naught is equal to VD is equal to 10 volts, that point. Then V naught is equal to minus VD, which is equal to 10 volts. And V naught is equal to minus VD is equal to 5 volts. That is at the intersections of the load line with the diode characteristic, curve, right? Though I will not examine you by using these graphs, but you should also be able to interpret those graphs just in case you are given such questions, right? Notice that the regulator is effective only for values of the load current up to 50 milliamps, right? That's where you can still have proper DC load line. Then after that, it goes out of range and it will not be able to regulate. Okay. So, because of our time, we'll take a break, 5 minutes break. You can leave the class and come back within exactly 5 minutes. That is at exactly 2 o'clock. No, at exactly 10 minutes to 2. I'm just stopping this so that we can restart the class. Our time is expiring now. Okay.